Area Navigation, RNAV. Area Navigation, or RNAV, pronounced RNAV, is a navigational process allowing point-to-point navigation without requiring that you overfly any navigational aids. Simply stated, if you have RNAV equipment on board, you can fly direct from one airport to another without having to follow traditional navigational routes. In other words, airways. While airways are nice to have, they are not always the fastest route between two places. They often don't connect the places between which you desire to travel, at least not directly. Instead of your path being a string directly connecting the 2 points, following airways can make your route look more like a piece of spaghetti that's been used to play crack the whip. Pilots are odd creatures. They love to fly, which should mean they want to spend as long as they can in the air, which they do. Except they always want to get where they're going as quickly as possible. Yes, it is a contradiction. RNAV offers the opportunity to pull the string taut and get from point A to point B by the most direct route possible. RNAV can be accomplished with any of 3 radio navigational devices: VOR-DME, LORAN, and Global Positioning System, GPS or satellite. Let's see what each of these does. RNAV based on VOR-DME. One of the earliest types of RNAV equipment uses VOR to create movable, artificial navigational stations known as waypoints. Using typical RNAV equipment, shown in Figure 28, pilots create an artificial VOR or waypoint using a radial and DME distance from another real VOR station. For example, suppose you wanted to fly direct between Where Are We Airport and Need Help Airport, as shown in Figure 29. To do so, you would create a waypoint using the Sinbad VORTAC. Ideally, you would locate this waypoint, in other words the artificial VOR, directly over Need Help Airport. This waypoint would be identified by the 160-degree radial and the 42 nautical mile distance from the Sinbad VORTAC. Set your RNAV equipment to the Sinbad VOR, selecting your first waypoint to lie at 160 degrees and 42 miles. Now you've programmed the RNAV equipment to pretend there is a VOR at this radial and distance point. Your RNAV equipment electronically creates an artificial VOR at this position. As far as your on-board VOR equipment is concerned, there is a real VOR at this waypoint. It can't distinguish the difference. Your VOR equipment provides you with the appropriate needle and flag movement in reference to waypoint number 1. With many RNAV units, you can create several waypoints at a time, waypoint 2, waypoint 3, etc., although 1 is plenty for this flight. Prior to departure, make sure your RNAV equipment is in the proper mode so that its navigational information is sent to the VOR's cockpit display. Check your equipment manual to determine how to do this. It's often just the throw of a switch which sets the VOR face to read from the RNAV unit. As soon as you are airborne, rotate the OBS, center the needle with a 2 indication, and track directly to waypoint number 1, located on Need Help Airport. Your VOR and DME will work as if a mobile VOR-DME station on a flatbed truck was driven onto the field at Need Help Airport. Figure 30 provides another way of understanding how RNAV works. For longer flights, additional waypoints may be necessary. Figure 31 shows a flight with 3 waypoints used to define the route. You would fly to waypoint number 1, then, when over it, fly outbound from it until midway to waypoint number 2. Then you would select waypoint number 2 in your RNAV equipment and fly to it, repeating the same process. There are some nifty little tricks you can do with RNAV, like pulling one out from behind the ear of an FAA inspector. Just kidding. You might create a waypoint on the highest mountain in the area. If you're interested in your distance from the peak, you would simply switch to that waypoint and read the distance on your DME. If you had an RMI, the needle would point to that waypoint, indicating the position of high terrain. This becomes even more helpful at night. If you're departing at night from an airport surrounded by higher terrain, create a waypoint on the field and circle around it within a radius of a few miles as you climb. This is sure to keep you away from higher terrain as you ascend. Remember, it's called night because it's dark out there. Flying too close to mountain peaks at night always causes a picture of the Last Supper to flash before my eyes. Pilots also use RNAV to help define borders of restricted and prohibited areas. These are just a few of the interesting uses of RNAV. Loran.
It's a plane. It's a train. It's a boat? No, it's a plane. The confusion arises because in the last few years, aviation has become a major user of LORAN, a system of navigational assistance originally established for the wet set, rather than the jet set. LORAN, or Long Range Navigation System, is a worldwide system of very low frequency signals used primarily for maritime purposes. Figure 32 shows a typical LORAN unit. LORAN is an example of the tremendous impact the electronics revolution has had on aviation. The original LORAN units were too bulky and slow for aviation use, though they worked just fine in boats. As microprocessors became faster, cheaper, and more capable, the cost of LORAN units plummeted, and their size and weight decreased, making them more feasible for small aircraft. Today, it's not unusual to find a LORAN unit in even a basic trainer airplane.
The beauty of LORAN is that all points are waypoints. Literally, every point on Earth defined by latitude and longitude is a LORAN waypoint. In the earliest aviation units, it was necessary to program most locations by entering latitude and longitude, which was laborious. Today, almost all units have a database which stores the position of every airport in the country or the world, all the VORs and other nav aids, and all or many of the electronically defined intersections on which instrument navigation relies.
Hey there, Sammy. It's a little-known fact, when aviation first started making the use of LORAN, there were problems receiving a usable signal in certain areas of the country. Remember, LORAN was built for boaters and the military doing ocean navigation. And nobody cared whether the signal was useful in Utah or powerful in Pittsburgh. Just as there was a missile gap and a front tooth gap, we suffered through an era with what became known as a mid-continent gap.
Awakened by the thundering sound of pilots demanding the advantages of LORAN, the FAA and the Coast Guard eventually got together to create additional LORAN transmitting stations placed in such a way as to fill the mid-continent gap. Considering its small size and price, an airborne LORAN unit is truly a marvel of modern electronics. It receives signals from at least 3 stations simultaneously, and from the tiniest of differences in the time at which the signals arrive, it calculates exactly where it is, and therefore where you are, assuming you've stayed with the plane. Pretty neat, isn't it? Well, that's not all. If you know where you were a minute ago, and you know where you are now, you can tell how far you've traveled in a unit of time. In other words, you can calculate your speed. So, LORAN not only provides information about where you are, but it also tells you your ground speed. Since it knows where it is, if you tell it where you'd like to go, a LORAN can tell you quite precisely 1. The heading to fly to get there in a straight line, 2. how fast you're getting there, and 3, how long it will take to get there at your current speed. In fact, Loran can provide you with so much exciting information, it will knock your wheel pants off. Loran can provide you with your ground track, the direction of the actual path made over the ground as opposed to the direction you have the aeroplane's nose pointed. It can tell you wind direction and velocity at your altitude, and with a push of a button, it can direct you to the nearest airport. Some Loran sets even provide an early warning when you're about to penetrate special use or clearance required airspace. It's a wonder that 2 little hands don't pop out of the equipment and fly the aeroplane for you. As I mentioned, most modern Lorans have extensive databases, and you may never need to program a lat-long heading. However, if you want to go someplace that isn't in the database, just enter the latitude and longitude information, and the Loran will tell you how to get there. If you're traveling in an area not covered by the database in your Loran, or are flying with an older unit that doesn't have a database, the Airport Facility Directory contains lat-long information for all U.S. airports. See Figure 33. Make no mistake, Loran is great. You should, however, be aware it does have a couple of limitations. There are circumstances under which the Loran signal is distorted. Rain can cause distortion and inaccuracy. So can travel near water. It's sometimes necessary to enter a correction factor if you're in an area adjacent to the coastline. These minor notes aside, Loran is a great means of getting where you're going with accuracy to within a few thousand feet. It's hard to believe it could get any better, but no sooner had the mid-continent gap been filled in than something better started to appear. The Global Positioning System, GPS. It's a bird, it's a plane, it's a satellite. Start the 2001 theme. Beam me up, Scotty. We now glide from science fiction to science fact. You can today, at low cost and no fuss, navigate using satellites, and more pilots are doing it every day. There is no doubt that the Global Positioning System, GPS, will soon be the dominant form of navigation worldwide. Originally developed by and for the military, GPS was radio-napped by the civilian population. It's easy to understand why. GPS provides highly accurate position information, a signal that's subject to very little distortion, and certainly no line-of-sight problems. Besides that, it's cool. GPS is in many ways like taking all the ground-based Loran stations and launching them into orbit. The receiver in your airplane or in your hand locks onto signals from several satellites all at once. By knowing the exact location of each satellite and precisely matching timing with its onboard atomic clock, the GPS receiver can figure out where it is and do so with an accuracy of less than 100 feet. Let's put it this way. If you manage to get lost while using GPS, then you're really lost. For your GPS receiver to determine a 3-dimensional fix, latitude, longitude, and altitude, at least 4 satellites must be in view, although a minimum of 5 satellites are usually in view by a user anywhere on Earth. The receiver can compute its position with only 3 satellites in view, but it must be provided with altitude information to do so.
GPS is much more accurate than Loran and isn't nearly as affected by atmospheric conditions. As a student of Rod said, "Whoa, dude, like with GPS, you know exactly where you're lost at. Sweet." Rod looked at him and said, "Hey, just because your friends say weird things doesn't mean you have to."
Not only does GPS locate your latitude and longitude position, it can also locate you vertically. In other words, provide altitude information above sea level. Figure 34 shows a typical GPS system and a few of its associated satellites. GPS can do everything Loran does for you and more. GPS waypoints are latitude and longitude based. For instance, if you wanted to fly cross-country on a flight from Rhodes Municipal Airport to Bob's International Airport, you might program your GPS unit for 2 waypoints as shown in Figure 35. Waypoint number 1 takes you to the outside of the restricted area, and waypoint number 2 is located at Bob's International Airport. After departure, you'd fly directly to waypoint number 1, thus avoiding the restricted area. Then you'd fly directly to Bob's International Airport on waypoint number 2. With GPS, you don't track from a waypoint, you only track to it. On GPS units, you see bearing, track, and distance information as shown in Figure 36, but you don't see any to or from flags. Once over a waypoint, you select the next waypoint along your navigation route. One of the things that distinguishes GPS from Loran or VOR-based RNAV is that GPS works everywhere on the planet. Its operation is virtually unaffected by distance from the station, thank goodness, since the station is in outer space, location, or weather. You can be put out in the Sahara Desert or on top of Everest and still obtain accurate GPS signals for navigation. Of course, if you're on the top of Mount Everest, you shouldn't need GPS to tell you where you are. In fact, many backpackers now carry handheld GPS units. A friend of mine has a small Cherokee 140 with 3 VORs, 2 Lorans, and a GPS system on board. He parks his airplane at Long Beach International Airport, goes away for 2 days, comes back, and can't remember where he parked his plane. He needs GPS to tell him where his airplane is. I promised I would never mention anything about this, so please don't tell anyone. Automatic Direction Finding, ADF, Navigation. Well, I've left the first for last. Automatic Direction Finding, ADF, equipment is the oldest type of radio navigational aid still in use. It is not cool, it is not slick, it is not particularly precise, but it is found in many airplanes, from trainers to jumbo jets, and it's a major item in places such as Alaska, where VORs are about as frequent as housebroken caribou. ADF has persisted because of its simplicity and reliability. Because it operates on a relatively low frequency, i.e. long wavelength signal, ADF can travel very long distances. It isn't subject to the line-of-sight limitations of VOR, and you don't need very sophisticated equipment to decode it. Perhaps the real reason ADF has persisted, though, is that it receives standard AM broadcast frequencies, enabling you to hear the baseball game or country in western Wales while en route. You'll see why this is of more than obvious significance in a second. Figure 37 shows a typical ADF set. Airborne ADF equipment consists of a rotating needle resting over a fixed or manually rotated compass card. The needle always points to a non-directional beacon, NDB, which is the source of the ADF signal. It's a non-directional beacon because the signal is radiated equally in all directions. There are no NDB radials. There is one other source of signals for your ADF. Yep, those radio stations playing that country music or the baseball game. If you can receive it on the ADF, you can fly to it. Every AM radio station in the country is an unofficial, non-directional beacon. During a cross-country flight, one of my students insisted on listening to ball scores over the ADF. I called the flight service station for a weather update. The flight service station specialist delivered a less than happy weather forecast, then heard my student yelling at his favorite team in the background. "Ah, for crying out loud, you can do better than that, sheesh." "Hey, I only report the weather, I don't make it," the specialist said. Since even the smallest of towns usually has a radio station, you can home in on almost anywhere using the ADF. Homing is exactly what ADF does. In no-frills terms, ADF takes you to the transmitting station, the NDB. Enter the frequency for an NDB where or near where you want to go, then turn the airplane until the ADF needle is pointing straight ahead. Follow it. When the needle gets erratic, then swings back in the opposite direction, you've just flown over the NDB, or station WXYZ. There are a few subtle details, but if you get the concept that the needle points like a good hound dog on the trail of Porky the Pig, you've got the basics. Tune in and aim it. Figure 37 shows a modern ADF unit with two frequencies selected, 341 kHz, thousands of cycles per second, and 256 kHz. One frequency, 341 kHz, is in use and the other, 256 kHz, is set for standby use. Many older ADFs you encounter will have three windows into which you dial the three numbers of the frequency you want, using mechanical switches.
Several other switches are present on typical ADF equipment. The switch marked ADF activates the ADF function. Sometimes things actually are what they say they are. The needle will point to the NDB or radio station, and you will hear the station's audio transmission. Pilots often listen for the Morse code identification of the NDB as their only means of knowing the station is on the air. Radio stations, of course, transmit rock and roll instead of Morse code. ADFs don't have off flags to warn the pilot of signal reception loss. You can electronically disconnect the needle from the circuitry and still listen to NDB transmissions by selecting the ANT or antenna position. Last but not least, if you're looking for a good reason to keep the ADF in your airplane, remember this. The ADF needle can point to the location of those big airplane catching radio antennas, assuming you've tuned your ADF equipment to their transmissions. The test position allows you to determine if the ADF needle is indeed pointing to any NDB or simply drifting without being locked onto a transmission.
ADF antennas are easy to spot on the airplane. They're usually a long wire strung almost from end to end on the airplane. The long wire is needed to receive the longer wavelength signal, as opposed to the higher frequencies used by VOR, DME, and other radio navigational gear. The long, wire-type antenna shown in Figure 38 is the signal antenna. Underneath the aircraft is a loop antenna, Figure 39. The antenna establishes a signal direction. Sometimes both of these antennas are combined in a single unit. Figure 40A and 40B shows how NDBs, low frequency, and radio stations, medium frequency, appear on aeronautical charts. Not all radio stations are charted, I hasten to add, only the ones with good baseball games or bad country and western. NDBs appear as concentric rings of expanding dots, normally red in color, as shown in Figure 40A. Frequency and identification information is shown in the accompanying rectangular box. Commercial broadcast stations with their associated frequencies appear as shown in Figure 40B. Remember, you never know when you might need the ADF for navigation assistance. Are we where yet? Good job. You've gotten oriented. By now you certainly won't pardon the pun. To the basic types of radio navigational equipment you're likely to meet. Now you're ready to learn something about the weather, which can often keep you from getting to all the wonderful places your equipment can take you. Post-flight briefing number 11-1. VOR reverse sensing. Reverse sensing occurs when you try to go to a VOR with a from indication, or vice versa. If you try to do this, the VOR needle will work opposite, in other words, reverse, of the way it normally does. In other words, if the selected course is shown to the left, it's actually to the right of the aeroplane. Figure 41 shows how this could happen. Assume you have been instructed to fly outbound on the 050-degree course from DLP VOR to NITO intersection, as shown by aeroplane A. At NITO, you are to track to the LHD VOR on the 320-degree course, the reciprocal of the 140-degree course from the station. You only have one VOR in the aircraft, and it's initially set to the DLP VOR with 050 degrees set in the OBS as shown by aeroplane A. When you suspect that you are near NITO intersection, you tune in the 140-degree course from the LHD VOR on your OBS as shown by aeroplane B. Remember, most pilots prefer to know their position from someplace when identifying an intersection with a VOR. There's nothing wrong with this, but watch what happens as your airplane approaches NITO with your VOR tuned to the LHD VOR and the OBS set to 140 degrees. The VOR needle starts to center as shown by airplane B. As it does, most pilots will turn toward the LHD VOR, attempting to fly the 140-degree course to LHD as shown by aeroplane C. The problem is that they often forget to rotate their OBS from 140 to 320, the 180-degree reciprocal, which selects the same course to the station instead of from the station. If wind blows the aeroplane slightly southwest of the 320-degree course to the station as shown by aeroplane D, the needle shows a left deflection. This is reverse from the way it should be. The pilot may fly left, thinking he or she will intercept the 320-degree route to LHD. Remember, if you're going to a VOR, the to from flag should read to, not from. The heading you're flying and the course you've selected by the OBS should be similar, not 180 degrees in error. If the pilot is slightly northeast of the route as shown by aeroplane E, the VOR shows a right needle with a from indication. This needle and flag indication makes sense if the aeroplane is heading 140 degrees. The pilots of aeroplane E will probably turn right, attempting to capture the route. You shouldn't need a burning bush to tell you that the most important rule in VOR navigation is the heading you are flying should be very similar to the number set by the OBS. When flying a specific route to or from a VOR, there is one time when the heading and the OBS setting won't be precisely the same: when wind exists. Post-flight briefing number 11-2. The radio magnetic indicator, RMI. Ever been in a Chinese restaurant with a large group? You get the food on a huge lazy Susan. The food spins round and round, the sauce stands still in the middle, and you pick what you want. It's an egg roll on a roll, wonton on a turn. The radiomagnetic indicator, RMI, is the aviation version of this device. What it serves up is information. While not common in smaller GA aircraft, if you are fortunate enough to fly in something that has an RMI, you'll want to make full use of it. An RMI is essentially a rotating needle mounted over a slaved compass as shown in Figure 42. A slaved compass is one where the rotating compass card is electronically connected to a magnetic compass. The rotating needle is slaved to the compass card so that it always indicates the course to the VOR station with the head of the needle. The tail of the needle points to the course or radial from the station. The slaved compass card rotates like a heading indicator would. The aeroplane's heading can be found under the index at the top of the RMI. The RMI needle information is correct only if the slaved compass is correct. Check it against the wet compass occasionally. The easiest way to learn how to use the RMI is to observe how the instrument's display orients you to a VOR station. Aeroplane A in Figure 43 is on a heading of 060 degrees, as indicated by the RMI's slaved compass. The RMI needle is pointing directly to the VOR station. Notice that Aeroplane A is physically located on the 360-degree course to the station, or the 180-degree radial from the station. Also notice the RMI needle points to 360 degrees on the slaved compass, and the tail points to 180 degrees. Okay, can you feel those neurons firing and synapses welding to form new ideas? This is really easy. The RMI needle always points to the course to the VOR station. The tail of the RMI needle always points to the radial you're on from this station. What course is Aeroplane C on to the station? Yes, it's on the 180-degree course, needle's head, to the station, and the 360-degree radial, the needle's tail, from the station. Of course, Aeroplane C is flying a heading of 300 degrees and will fly right across the 360-degree radial from the station. Aeroplane B, on the other hand, is headed directly toward the station on a heading of 270 degrees. Its RMI needle is pointing dead ahead at 270 degrees. Aeroplane B is headed to the station on the 270-degree course, or inbound on the 090-degree radial, the same thing. Aeroplane D is headed toward the station on the 090-degree course, or inbound on the 270-degree radial, also the same thing. Orientation with the RMI is really simple. If you want to know what your course is to the station, just look at the number to which the RMI needle points. If you want to know what radial you're on from the station, simply look at the tail of the RMI needle. One last thing. Sometimes RMIs have two needles instead of one. To keep them from being confused with one another, the second needle is different, as shown in Figure 44. Each needle can be selected to represent VOR or ADF information. This is accomplished by the selecting switches at the bottom of the instrument. We'll learn more about RMI usage when we cover ADF navigation next. Before I begin post-flight briefing number 11-3, let me say that I was tempted to eliminate most of the ADF information that follows from this book. Really tempted. Frankly, if you know how to determine the relative bearing and magnetic bearing to a station by using the formula on page K34, you can answer 99% of the knowledge exam questions on ADF. I'm leaving the information in simply because if you take the time to understand ADF principles, you'll never have trouble with any type of navigation. Post-flight briefing number 11-3. ADF, bearing down on homing in. Look at the numbers on the compass card of the ADF display in Figure 45. They're fixed, in that the card doesn't automatically rotate like the compass card of an RMI. You can manually rotate the card, as we'll discuss later. For now, however, forget those numbers. Yes, that's right, forget them. As far as you're concerned right now, those numbers only identify 30-degree incremental positions to the left and right of the nose. Don't attach any significance to them. Treat each of these numbers like most people treat the Surgeon General's warnings on a cigarette package. Know that it's there, but don't look at it. Okay, here is one of the most powerful and most simple rules you'll ever see for navigation with the ADF. To go to any NDB station, simply tune in that station's frequency, identify it, usually by Morse code, and turn the aeroplane so the ADF needle points to the nose of the symbolic aeroplane on the ADF display as shown in Figure 46, aeroplanes A and B. The symbolic aeroplane represents the real aeroplane's orientation. It's always pointed toward the white triangle at the top of the ADF indicator, which represents the aeroplane's nose. Simply turn toward the tip of the needle to go to the station. If you keep the needle centered at the top of the display, you will eventually end up over the station. As you fly over the station, the needle will swing to the tail as shown by aeroplane C in Figure 46. This type of tracking is known as homing. It involves no wind correction, but it works every single time. Don't forget it. Figure 47 shows aeroplanes A, B, and C homing directly to the Fly Nice NDB. Aeroplane E is flying directly away from the station by keeping the needle on the tail of the ADF display. Aeroplane D's ADF needle points to the left of the nose. Making a left turn will center the needle at the top of the display. Aeroplane F's ADF needle shows the NDB station to the right of the aeroplane's nose. Turning right will center the needle at the top of the display.
Now, boys, if Rod had his way, we'd stop here and consider ourselves done with ADF discussion. All you really need to understand about ADF navigation is to know how to home with it. The private pilot knowledge exam, however, demands a slightly more sophisticated knowledge of ADF navigation. Study the following and find some solace in knowing that this information will help you become an overall better navigator. Not a navigator who wears overalls. No, say. Just think of all us NDBs working together to achieve a common cause.
Tracking a magnetic bearing. Homing is the easiest method of ADF navigation. Perhaps it's called homing because pilots can always find their way home using this technique. There is another method, however, that allows you to intercept and track magnetic bearings directly to and from an NDB. This is done in much the same way as the RMI is used. Let's start from the beginning. Figure 48 shows an NDB and a VOR station. NDBs are unlike VORs in that their signal is non-directional. This means the NDB's signal radiates outward in all directions, while VORs have 360 specific radials on which we can navigate. We can, however, imagine 360 bearings running through an NDB in much the same way courses run through a VOR. First, we need to define what a bearing is. Examine the diagram in Figure 49. If you were instructed to fly from position A directly to position B, you could do so with great precision by using the VOR. You would track inbound on the 270-degree radial and outbound on the 090-degree radial. You would know your exact position with respect to these radials by looking at the VOR needle. Suppose you were asked to fly from position X directly to position Y using your ADF. How would you know your airplane is tracking directly along the specified course? You need to know two things before answering this question. First, the airplane must be heading in a direction of 90 degrees. We'll assume no wind for these examples. Heading 90 degrees will certainly point you in the direction of location Y, as shown in Figure 50A. However, heading 90 degrees will also allow you to fly a parallel course, offset from the originally desired path, as shown in Figure 50B. We need one additional bit of information. If the ADF needle points to the nose of the display aeroplane while it is heading 090 degrees, then it is precisely on the course from X to Y as shown in Figure 50C. After crossing the NDB station in Figure 50C, the aeroplane will begin flying the desired course to Y if its heading is 090 degrees, and the ADF needle points directly to the tail. Aeroplanes flying a parallel route between X and Y in Figure 50D don't meet both requirements to be on the specific course. In Figure 50D, both aeroplanes flying from X to Y are heading 090 degrees, but the ADF needle points somewhere other than to the nose or the tail. A very important principle has just been uncovered. Even though NDBs are non-directional in their signals, we can still fly specific directional routes using the ADF and our heading indicator. These routes are called magnetic bearings, and they may be flown to or from an NDB. Figure 51 shows several aeroplanes, all of which are on specific magnetic bearings to and from a station. Aeroplane A is heading 270 degrees with an ADF needle pointed to its nose. It's on the 270 degree magnetic bearing to the station. Aeroplane B is on the 045 degree magnetic bearing from the station, and Aeroplane C is on the 135 degree magnetic bearing to the station. Of course, we don't have two from and off flags on an ADF. It should be obvious whether you're going towards or away from any station, since the needle is pointed either to the nose or the tail of the ADF's compass card. Aeroplane D is flying the 225 degree magnetic bearing from the NDB, and Aeroplane E is on the 180 degree magnetic bearing from the NDB. Make sure you understand this important principle. When the needle is pointed directly to the nose or the tail of the ADF, the direction the aeroplane is heading is also its magnetic bearing to or from the NDB. We're still assuming a no-wind condition, by the way. Now you're ready for two nifty techniques. First, I'm going to show you how to use the ADF's rotating compass card to identify the bearing you're on to or from an NDB. You'll do a backflip when you see how easy this is. Second, I'll show you an easy formula you can use to solve any written test question concerning ADF navigation, and there will be some, I can promise you that. The ADF's movable compass card. I'll have to admit that practical jokes run in my family. Many years ago, my girlfriend wanted me to take her out for her birthday. She said she didn't care where we went as long as it was expensive. I took her to the airport for a sandwich. I promised we'd do something really exciting after dinner. I got out my blackboard and started to describe how to use the ADF's movable compass card. She loved it, but not me. But you'll probably love it, if not me, when you see how easy the movable compass card makes ADF navigation. Most ADFs have numbered compass face cards that rotate. Let's examine the utility of this manually rotating compass card, as shown in Figure 52. A rotating compass card allows you to set the aeroplane's heading under the heading index, white triangle, at the top of the instrument. Unfortunately, unlike the RMI, which has a slaved gyro compass, the movable ADF card must be manually rotated to the aeroplane's current heading. Nevertheless, it has a practical use. Rotating the ADF compass card to the aeroplane's heading results in the needle pointing to the bearing the aeroplane is on to or from the NDB. The ADF's needle is then interpreted in exactly the same way as the RMI's needle. If you manually rotate the ADF card to the aeroplane's magnetic heading of 090 degrees, the ADF needle always points to a number that's the magnetic bearing to the NDB. That's right. Now, and only now, it is okay to pay attention to the numbers on the face of the ADF card. Aeroplane A, in Figure 53, is on the 060 magnetic bearing to the NDB. Aeroplane B is on the 360 degree, or 0 degree, bearing to the NDB, and aeroplane C is on the 300 degree bearing to the NDB. Pretty easy to use, isn't it? If you were instructed to identify crossing the 360 degree bearing to the NDB, you would wait until the ADF needle pointed to 360 degrees or 0 degrees. If you were in aeroplane A, you would know you hadn't crossed the 360 degree magnetic bearing to the station, since the needle doesn't point to 360 degrees. You know you will eventually cross the bearing if your heading is held constant. Why? Because the ADF needle always moves towards the tail if your heading is constant. Any NDB station in front of you will always end up behind you if you hold a constant heading. Aeroplane C has flown beyond the 360 degree bearing to the NDB because the head, or the point, of the ADF needle has fallen past the 360 value on the ADF's card. That needle will not move back up as long as the aeroplane's heading is maintained. These same procedures apply when intercepting a magnetic bearing from the NDB with a movable ADF card. In Figure 54, aeroplanes A, B, and C are on a magnetic heading of 320 degrees. Suppose you are asked to report crossing the 020 degree magnetic bearing from the station. The movable compass card has been rotated so that your heading of 320 degrees is set to the top of the compass card. How will you know when you're crossing the desired bearing? You'll know when the tail of the ADF needle points to 020 degrees, as is shown by aeroplane B. In this instance, the tail of the ADF's needle points to the magnetic bearing from the NDB. Of course, aeroplane C has flown beyond the 020 degree bearing. How do you know? If the head of the ADF needle always moves aft under a constant heading, the tail can only rise. There's no room for argument here. Head falls, tail rises. The tail of aeroplane C's ADF needle has risen above 020, and it certainly won't move back down. Knowing the ADF tail will rise allows you to determine what magnetic bearing you'll intercept from any NDB station. The only problem with using a movable compass card is that you must constantly keep twisting it as your heading changes.
Hey, you can't believe everything you hear. A friend of Rod's told him that watching fish is relaxing. Well, that surely explains why Rod dozes off when snorkeling. You can, however, believe ADF navigation is made very simple when you use the rotating compass card to help determine your magnetic bearing to and from the station.
The ADF fixed compass card. At the very beginning of our discussion, I said to think about the numbers on the ADF's fixed card as index marks. I didn't want you to think they represented anything useful at that stage of this presentation. However, the numbers on the fixed card, the card with the 0 set at the top, do have value, especially when solving knowledge exam questions. The following information is for doing just that, answering written test questions only. Don't attempt to navigate this way in an airplane. It's just not practical. If you do try it in the air, I guarantee your mind will come to a stop quicker than a lawnmower cruising over a tree stump. We only do practical things in aeroplanes. It's like the old sage advice to yell fire if you're being attacked. This surely works a lot better than help, this guy has a gun. First, let's define a few terms. The relative bearing is not a round metal ball underneath your Aunt Mabel. It is the actual number the needle points to on the face of the ADF's fixed compass card. It's called relative because it's measured clockwise from 0 degree to 360 degrees to the right of the nose. In other words, if the needle were pointed 10 degrees left of the top of the compass card, as in figure 55, we would say its relative bearing is 350 degrees. ADF card B shows a relative bearing of 70 degrees, card C shows a relative bearing of 270 degrees, and card D shows a relative bearing of 330 degrees. Remember, relative bearings are relative or counted to the right of the top or the nose of the ADF compass card. During a written test, there is a nifty way to find your bearing to the NDB station using the relative bearing and the aeroplane's magnetic heading. By adding the relative bearing shown on the face of the ADF compass card to the aeroplane's magnetic heading found on the heading indicator, you can find your magnetic bearing to the NDB. In other words, RB plus MH equals MBTS, which stands for relative bearing plus magnetic heading equals magnetic bearing to the station.
Don't be scared. This is a very simple math formula. I know. Many people have difficulty with math. In fact, a friend of Rod's, who has math phobia, once said, "Hey Rod, did you know that 5 out of 4 people have trouble with math?" As you can see, Rod's friend really has trouble with math.
To understand how to use this formula, examine figure 56. Aeroplane A has a relative bearing of 080 degrees shown on the face of its ADF compass card. Its heading is 310 degrees. Use this formula to find its magnetic bearing to the station. First we add RB plus MH equals MBTS, or 080 degrees plus 310 degrees equals 390 degrees, the magnetic bearing to the station. As we've previously learned, any magnetic bearing greater than 360 degrees means a complete circle has already been made, and the heading count should begin anew. In our example, we'll subtract 360 degrees from 390 degrees, leaving us with 30-degree magnetic bearing to the station, as depicted in figure 56. Suppose we wanted to know our magnetic bearing from the station. Simply add or subtract 180 degrees from the bearing to the station to get its reciprocal. If we are on the 030-degree magnetic bearing to the station, the magnetic bearing from the station is 30 degree plus 180 degrees, equaling 210 degrees. What is the magnetic bearing to the station of aeroplane B in figure 56? Adding the relative bearing of 300 degrees to a magnetic heading of 270 degrees gives us a magnetic bearing to the station of 210 degrees. We arrived at that by 570, which is the total of 270 and 300 minus 360. Your answer always has to be 360 or less. What is aeroplane B's magnetic bearing from the station? Simply subtract 180 degrees from 210 degrees to get 030 degrees, as shown in figure 56. Would you ever use this formula in flight? Probably not. I have never met a competent pilot who pulled out his abacus and started flipping beads to find his location with an ADF. I have, however, met some who used beads to pray with because they didn't have an easy way to solve knowledge exam questions. Chapter 12. Understanding Weather. Looking for Friendly Skies. Introduction.
An airline pilot was 7 miles from the airport on approach to Lambert Field in St. Louis when he made his first call to the air traffic control tower. Lambert Tower, this is TWA 413, outer marker inbound, over. No reply came from the tower. Lambert Tower, this is TWA 413, outer marker inbound, over. The tower controller still didn't respond. Lambert Tower, this is TWA 413, how do you hear, over? Finally, the tower controller replied. TWA 413, this is Lambert Tower. Please stand by, we're changing controllers down here. Meaning a controller shift change. Not wanting to miss an opportunity, the TWA pilot replied, Lambert Tower, this is TWA 413. Tell me, what do you folks use, Huggies or Pampers? Everyone had a good laugh as the airliner landed uneventfully. Isn't it interesting that the tower controllers and pilots get along with each other despite the tensions and anxieties of their jobs? Sure, there are moments of frustration, but it ultimately works because of knowledge and understanding.
Knowledge and understanding is exactly what you need in order to cope with another relationship, the one you as a pilot must have with the weather. Unlike most relationships, this isn't one you have a whole lot of choice about. If you fly, you will face weather, unless you confine your flying to outside the atmosphere. Learning about the weather and your relationship to it is what we're setting out to accomplish in this chapter. As a bonus, when you graduate from this chapter, you will be able to really understand what the person on the eyewitness news is doodling on the weather map. Weather accounts for 25% of the aviation accidents and almost 40% of all aviation fatalities. Getting along with the weather machine is essential for safe, successful flying. As with all relationships, understanding the other party allows us to survive and thrive in a comfortable, safe atmosphere. Understanding meteorological forces begins with identifying how uneven heat distribution across the planet's surface creates weather. Atmospheric circulation. I will now teach you the basics of weather. 1. Air is heated unevenly by incoming solar radiation. 2. Heated air rises and moves. That's it. The rest is just filling in the details. Class almost dismissed. And you thought learning about weather was difficult. Uneven heating is the ultimate weather engine. It's what makes weather go. It causes rain, wind, thunder, clouds, and all the other excitement that makes up the weather show on Earth. Have you ever seen a cat on a metal roof in summer? There was once a play about it, Cat on a Hot Tin Roof. Instead of pussyfooting around, the animal stays on the move. Air does the same. It's air today, gone tomorrow, moving restlessly around the Earth in a never-ending and futile attempt to evenly distribute heat. As the air moves, it creates the things we collectively refer to as weather. For the sake of discussion, let's assume our Earth doesn't rotate. Well, that's not true, just in case you're confused on the concept. I'll make the Earth move for you in a minute. Figure 1 shows how a portion of the Earth at the equator receives a great deal more solar heat than the area near the poles. Equatorial air, resting over a warmer surface, is eventually heated from below. Just like the cat's feet on a hot tin roof, the air becomes less dense and rises. The engine is running. Up to a certain altitude in the atmosphere, called the tropopause, temperature decreases with altitude. The heated air rises until it finds air of a similar temperature near the tropopause, position A. Once it's at equilibrium with the air around it, our restless parcel will stop rising, but it won't stop moving. Unable to ascend further, the air begins a journey north and south toward the poles, where it eventually cools and descends, position B. The airflow cycle in this simple illustration is complete when cold, descending polar air moves toward the equator, replacing the rising equatorial air, position C. This simple single-cell circulation would be the way things were if, and there always seems to be an if, the Earth didn't rotate. If the Earth didn't rotate, this would be the end of our discussion on atmospheric circulation, and this chapter would be incredibly short. The Earth, however, rotates, which literally introduces a new twist into the calculations. The Coriolis force. When viewed from above the North Pole, the counterclockwise rotation of the Earth causes air to curve or twist to its right, relative to the terrain in the northern hemisphere and to the left in the southern hemisphere. No matter which way the air moves, it will have a right curve or twist added to its direction of motion. Air is forced to curve by something known as the Coriolis force. This isn't a real force similar to that which you feel when a big thug punches you in the snoot. It's an apparent force. In other words, the Earth rotates under a moving parcel of air, which gives the air the appearance of being deflected to the right in the direction it was moving. What appears to be magic is actually sleight of land. You can demonstrate the Coriolis force quite nicely as shown in Figure 2. Simply take an old record. Ethel Merman records are easiest to find since they sell like hotcakes, $2 a stack. And spin it in the direction the Earth rotates, counterclockwise, as if you're looking down from over the North Pole. Have a friend hold a ruler 1/2 inch above the rotating record. Take a piece of chalk and move it along the straight edge of the ruler, drawing a line on the rotating surface. Do it first from the exact center outward as in position A. Then do it from the edge to the exact center as in position B. Finally, do it in a sideways direction as in positions C and D. After each marking, notice how the chalk path curves. Each path is curved to the right in the direction the chalk moves. No matter which way you moved that chalk, a right curve is apparently added to its motion. North of the equator, the Coriolis force curves the air to the right. South of the equator, the Coriolis force adds a left curve to the motion of the air. We'll limit our discussion to the events in the northern hemisphere.
Little, if any, movement escapes the effects of the Coriolis force. One-way railroad tracks experience more wear on the right side of the track than the left. Rockets, planes, spitballs, boats, and cars all, to some degree, experience the effects of the Coriolis force. Remember, no matter which way the air moves in the northern hemisphere, right, left, sideways, or diagonally, it will have an apparent right curve or twist added to it by the Coriolis force. An easy way to remember this is to recall the movie The Godfather. You might remember Don Coriolis. Actually, it's Corleone. If things weren't going right, he'd make them right by doing the right thing. Perhaps Don Coriolis would grab a tough guy's right arm and make him say uncle, then talk to him about fish heads, right? Hopefully, this will make it easier to associate the Coriolis force with a curve or twist to the right.
Now, let's take a look and see how the Coriolis force alters the simple, single-cell atmospheric circulation previously presented in Figure 1. In the northern hemisphere, rising warmer air is curved to the right in an easterly direction by the Coriolis force, Figure 3. Eventually, the high-altitude rising air moves in an easterly direction and starts to bunch up, much like a freeway crowded with cars. This bunching up occurs most noticeably at about 30° north latitude. As the air rises, some of its heat is lost through radiation during the ascent. Both bunching up and cooling cause some, not all, of this air to slowly descend at the 30° north latitude location shown in Figure 4, position A. Bunching up increases the air mass above and thus causes a higher surface pressure at the 30° latitude position. As the air descends toward the surface, it warms, causing clear skies usually, and warm surface temperatures. Some of this high-pressure air flows southward toward lower pressure at the equator, position E. The rest of this warm, low-altitude air at position D moves northward. Some of the high-altitude air that didn't descend at 30° latitude continues to move northward toward the pole, as shown by position B in Figure 5. As it continues to cool, it falls and travels southward from the North Pole, position F. At approximately the 60° north latitude, position G, this southward moving colder air meets the northward moving warmer air, position D. These two air masses have different temperatures and thus different densities. We know that things with different densities tend not to mix. For example, crude oil and water have different densities and certainly don't mix. That's why California, with all its oil spills, now has 3 different types of beaches: regular, super, and unleaded. When very cold polar air bumps into cool tropical air, the result is a transition zone, shown at position H. This zone is known as the polar front. A front is simply a zone where air masses with different densities meet. Some of the northward moving cool air flows upward over the colder, and therefore denser, polar air, position H. This ascending air is carried northward toward the pole with the rest of the high-altitude winds. 3 separate cells of circulation are now evident. In a while, we'll discuss fronts and their movement. Right now, just notice how winds in these 3 cells are affected by the Coriolis force. Figure 6 depicts a profile of these 3 individual circulation cells. Between 0 and 30° latitude, the northeast trade winds blow. From 30 to 60 degrees, the prevailing winds are westerlies, and from 60 to 90 degrees, the winds are the polar easterlies. Notice that meteorologists always talk about winds in terms of the direction they blow from, not to. Meteorologists do this because winds, like people, are better understood when you know their origins. If winds come from the north, they are likely to be cold. From the south, they are likely to be warm. If a mean-looking guy comes from a bad neighborhood, you know a lot about him. If he said he not only grew up on the wrong side of the tracks, but grew up underneath them, you know he was a bad dude. Figure 7 depicts this circulation on a multi-dimensional level. While the issue of air is weighing on your mind, let's see how it weighs on the Earth. Air pressure and vertical air movement. Air has weight. This weight exerts a pressure on the Earth's surface in much the same way a professional wrestler exerts pressure on your body by standing on your chest. I hope this doesn't happen to you a lot. Changing the air's temperature, however, changes its density and the pressure it exerts on the Earth's surface. For example, along the equator there exists areas of warmer, less dense, rising air, as shown in Figure 8, Position 1. Rising air certainly wouldn't create as much pressure on the surface as descending air. After all, one moves upward while the other pushes downward. Warmer, less dense rising air provides less push or pressure on the surface. We call large areas of warm rising air low-pressure centers. Near the equator, it's quite common to find permanent belts of low-pressure air wrapped around the Earth. Conversely, permanent high-pressure areas exist at the poles, Figure 8, Position 2. Colder, more dense air descends, creating more pressure on the Earth's surface. Now you know why cold air falls on your toes during those nocturnal refrigerator raids. Think of cold air as an anvil resting on your chest, as shown in Figure 9. Gravity pulls the anvil downward as it does with cold air, increasing the pressure on your body. Let's attach helium balloons to the anvil, making it lighter. Now the anvil moves upward off your chest, in the same manner as rising warmer air moves upward off the Earth's surface. Pressure at the surface decreases as warm air rises. Of course, as warm air rises, cold air moves in underneath to replace it. Thus, atmospheric circulation consists of high-pressure air moving toward lower-pressure air, Figure 8, Position 3. This simple air circulation model is a fundamental key to understanding weather. Now that you understand major wind patterns, it's time to examine exactly what makes the wind blow. Getting water in the air.
Weather, meaning clouds, rain, thunderstorms, etc., wouldn't exist if there wasn't a means of putting water into the air. Television meteorologists would be forced to entertain their flock with hand-puppet shadows and benign patter. Nearly half of all pilot fatalities would disappear, and any remaining flight service stations could be retrofitted as bowling alleys.
Weather is water. There's a good chance the room you're sitting in right now contains several pints of water suspended in the air. You can't see it, but it's there. It got there through one of two different processes: evaporation or sublimation. Either of these processes cause water molecules to absorb heat energy and enter the atmosphere. Water exists in three states: solid, in other words ice, liquid, and gas, or water vapor. Changing from ice to water vapor or water vapor to ice while bypassing the liquid state is known as sublimation. For instance, snow or ice can sublimate directly from a solid to a gaseous state. This increases the water vapor content of the atmosphere as shown in Figure 10. A more common means of adding water to the atmosphere is through evaporation. As water molecules absorb heat energy, they eventually become energetic enough to jump into the air, Figure 11. More heat means more evaporation. Given enough heat and a large enough water supply, the atmosphere can fill with water vapor. For a given temperature, however, the air can only hold a certain amount of water, just as a theater has only so many seats. The air is said to be saturated when additional water vapor is unable to enter the air. Saturated air is very much like the packed theater, in that no one else can get in without someone else leaving. The place is packed. The water content of warm and cold air. Anyone who has spent time along the eastern coast of Florida or the Texas Gulf Coast knows what humidity is. I once asked a friend what his summer visit to Houston was like. He replied, "Well, Rod, have you ever tried to breathe pound cake?" Apparently, he found the humidity stifling. Why are summers usually more humid than winters? Summers are generally more humid because the air is warmer to begin with. Warm air has the capacity to hold more water than colder air. Let's find out why. To understand why warm air can hold more water vapor than cold air, you need to understand a little quirk about water molecules. Unlike air molecules, water molecules like to cling to one another. This explains why you are more likely to find puddles of water than puddles of air on the ground. Water molecules are like aging, out-of-shape, one-too-many Twinkie-a-day prize-fighters who always seem to grab onto each other in the 14th round. Of course, they might do this simply because they like each other. Heating the air causes both air and water molecules to vibrate faster, Figure 12a. Water molecules that bounce and ricochet off each other with sufficient impact are less likely to stick together. Thus, you can put more water molecules into warmer air without them clinging to each other and forming clouds, also known as sky puddles. As the air cools, water molecules move slower and vibrate less, Figure 12b. Collisions between water molecules are now gentle enough to let them stick together. These clinging water molecules now become visible in the form of a cloud. In other words, the water molecules can't remain as vapor or gas, so they return to the liquid state in the form of something visible, a cloud. Additional cooling allows the water droplets to grow in size, as shown in Figure 12c.
The process of water vapor becoming visible is called condensation, and it results in the formation of fog or clouds. When water vapor condenses, it means that the air is saturated and can't hold any more water in vapor form. Now you know why cold air can hold less water vapor than warm air. It reaches its point of saturation sooner. Keep in mind that the process of condensation is the opposite of evaporation. When it comes to water, what goes around definitely comes around. This explains the mystery of the sweating glass. Why does a glass get damp on the outside when you pour cool lemonade in it on a hot summer day? Hot air, carrying lots of moisture, comes in contact with the cool surface of the glass. The suddenly chilled air can't hold its water. Do you recall your last flight on an air-conditioned airliner? Cool, wasn't it? Dry, too. Very dry. Air conditioning cools the air and dries it, making your eyes feel like tiny shriveled prunes rattling around in an oversized socket, just like the last tic-tac in the pack. Contact lenses dry and stick as if they've been arc welded to your corneas. This explains why several people on my last flight requested a ginger ale with a Visine chaser.
2 ways to cool air. There are 2 ways to cool air and condense water vapor. First, you can put the air in contact with a cooler surface or environment. Second, you can lift the air and let it cool by expansion. Let's examine the first process. Have you ever been to Minot, North Dakota in the winter? It's a beautiful place, but it's memorably cold. A preacher friend says that's where you'll find all God's frozen people. And that's why they call it Minot. You go there for one winter, and you may not want to go back. Talk with anyone on those cold winter mornings, and you'll see visible breath shafts, clouds, coming from their mouth, as shown in Figure 13. Warm air from their lungs contains a lot of moisture, As this warm air comes into contact with the colder surroundings, the breath shaft becomes saturated with water vapor, condensation occurs, and a cloud forms. This is how clouds form, by coming into contact with a cooler surface. An added benefit is that if the person speaking to you has bad breath, you can see it coming and take evasive action. Fog formation is often based on air coming into contact with a cooler surface. Water vapor condenses, forming visible moisture in the form of clouds that touch the ground. But what about clouds that don't touch the ground? How do clouds form in the atmosphere? If you lift air, you'll cool it. You'll have to go a bit farther than from your desktop to the top of your head to have any noticeable effect. So this isn't an experiment you can do at home. Rising air undergoes a decrease in pressure because of the decrease in weight, thus pressure, of the atmosphere above it. This is similar to the reduction in body pressure experienced when ascending from the bottom of a swimming pool. Air molecules expand when they are subject to less pressure. Since there is not another energy source available, the air molecules must use their own energy to expand. This slows them down, which results in a lower temperature. Air that rises always expands and cools. What happens to cooler air? It doesn't hold as much water as warmer air. Out it comes. This creates visible moisture in the form of clouds, as shown in Figure 14. In fact, air is not the only thing that expands as it ascends. The human body also does this. Decreasing air pressure with increasing altitude is one reason why flight attendants are told to wear looser clothing on the ground. Bodies expand slightly with altitude, making tight fits uncomfortable. I have never been trapped in pantyhose, honest. But I understand it's very uncomfortable. Fortunately, the process of condensation is rather predictable. Without Kreskin, Gene Dixon, or a Ouija board, we can still determine the temperature at which clouds begin to form. This is certainly a handy thing for pilots to know. Before we can do this, however, we need to know something about the percentage of water in the air, otherwise known as the relative humidity. Relative humidity. Relative humidity is not a description of your family, who are all wet. It's a number that tells us how much water vapor the air is holding in relationship to how much it could theoretically hold at its current temperature.
Rush hour in Los Angeles, California helps us visualize this. At 3 in the afternoon, each moving automobile on the freeway is spaced about 3 car lengths behind the next. With greater space between vehicles, it's easy to slip in and move with traffic, especially when no weapons are involved. It might be said that the freeway currently holds only 25%, one of a total capacity of 4, of the number of automobiles it's capable of holding. We might say the freeway's relative capacity is 25%. But what happens at 5 p.m.? Space between automobiles decreases until bumpers are nearly touching. The freeway is now 100% saturated with cars. No more will fit. Nothing is moving. Its relative capacity is now 100%. If a car tries to get onto the freeway, another has to go over the railing. Hey, it can happen. Likewise, evaporation or sublimation can add only so much moisture to the air before things reach a saturation point. And when the air is saturated, you're not going to coax any more water vapor into it. Evaporation or sublimation is just one way air becomes saturated, but it's not the most common way.
Cooling the air is the most common way for it to become saturated. Suppose air parcel A, in Figure 15, contains only half the moisture it's capable of holding. We can say this parcel is 50% saturated, relative to the amount of moisture it can hold at its current temperature. Another way of expressing this is to say its relative humidity is 50%. The numerical value of 50% is relative to that particular parcel of air only. What happens to the relative humidity when the air temperature decreases? Yes, the relative humidity goes up. It's just like the freeway losing a few lanes. It loses its capacity to handle traffic. When the temperature drops, the air loses its capacity to hold water. As air parcel B in Figure 15 is cooled, its water molecules start clinging to one another and begin to return to the liquid state. The air eventually becomes saturated and can't hold additional water molecules with further cooling. Parcel B's relative humidity has now increased to 100%. Condensation occurs, and water molecules are forced out of the air. Notice that the actual amount of water vapor and liquid in parcel B didn't change. Only the ability of the air parcel to hold additional water vapor has changed. While relative humidity informs us about the air's capacity to hold water vapor, it doesn't allow us to predict when clouds will form. After all, relative humidity just tells us the state of the air right now, not what it will be in the future. There is, however, a meteorological value known as the dew point, which provides us with cloud predicting ability. The dew point. The dew point is the temperature to which a parcel of air must be cooled to become 100% saturated. It's a predictor of when condensation will begin for a particular parcel of air. Assume a meteorologist, that's a weather person, not an asteroid technician, says the air's dew point is 60 degrees Fahrenheit. If our thermometer shows the air's temperature is 75 degrees Fahrenheit, then we immediately know the air is not completely saturated. In other words, its relative humidity is less than 100%. But cool the air down to its dew point of 60 degrees Fahrenheit, and the relative humidity increases to 100%. Condensation occurs, and fog or clouds form. Meteorologists refer to the actual temperature difference between the temperature and the dew point as the temperature-dew point spread. Sounds like a nifty name for a Texas cattle ranch. The process of condensation can actually begin about 5 degrees Fahrenheit, 2.8 degrees Celsius, before the air temperature cools to its dew point, otherwise stated as a temperature-dew point spread of 5 degrees. Dew points are handy numbers for pilots to have for several reasons. It's important to understand that the dew point is a great indicator of the atmosphere's water content. High dew point temperatures indicate a lot of water in the air. Low dew point temperatures indicate little water in the air. The temperature-dew point spread also tells you whether the humidity is high or low as well. Assume, for instance, you're planning a short flight to arrive at an airport about a half hour after sunset. Air temperature often drops noticeably at sunset, sometimes 10 to 15 degrees Fahrenheit or more within the first half hour. Your weather briefing shows the air temperature at the airport is 65 degrees Fahrenheit, and the dew point is 55 degrees Fahrenheit. Would you anticipate any problems? Despite a 10-degree Fahrenheit degree spread between the temperature, 65 degrees Fahrenheit, and the dew point, 55 degrees Fahrenheit, atmospheric cooling after sunset could easily drop the air's temperature to within 5 degrees of its dew point. That means fog or low clouds. Nothing is more frustrating for a VFR pilot than to navigate directly to where the airport should be, look down, and see the area covered by clouds. Be aware that fog or low cloud formation can even occur with temperature dew point spreads of as much as 6 degrees Fahrenheit. Also, water vapor condenses more easily when the air contains an abundance of airborne particles, also known as condensation nuclei. A large number of atmospheric particles makes it easier for very small particles of water vapor to collect, helping to form larger water drops. Airports downwind from an area of industry, in other words, smog equaling particulate matter, are more likely to have fog or low clouds form at larger temperature dew point spreads.
Did you know? Now this is true. Air in places like Los Angeles contain a lot of particulate matter. In the Los Angeles basin, it's not unusual for fog or low clouds to form at temperature dew point spreads of 6 degrees Fahrenheit. Not only are there salt crystals from the ocean suspended in the air, but dust and photochemical smog are often available in abundance. As one friend said, LA is a great place to be if you're a muffler. It is, however, a beautiful place. During a ceasefire, keep in mind the dew point varies with such items as geographic location and atmospheric pressure. It can change considerably during the day. A simple call to the flight service station, accessing a computer weather program, calling an air traffic control facility, hearing the ATIS broadcast, or listening to an automated weather observation station provides instant temperature dew point information.
Condensation and cloud formation. If clouds are present, does that mean it's going to rain? Definitely not. But if you have rain or some other form of precipitation, hail, snow, etc., clouds are definitely nearby. If you're driving along and see water coming from the sky without clouds, there's a good chance that you've just hit a fire hydrant or driven under an elephant. For significant precipitation to occur, clouds must generally be around 4,000 feet thick. Precipitation can take the form of rain, hail, snow, ice pellets or grains, or freezing rain. Essentially, precipitation is any or all forms of water particles, whether liquid or solid, that fall from the sky and reach the ground. It is distinguished from clouds, fog, or dew, in that it falls and makes contact with the Earth's surface. When flying near any airport reporting precipitation of light or greater intensity, expect clouds to be at least 4,000 feet thick. Lapse rates and temperature inversions. Suppose your family acquires an electric hedge clipper, and you're an only child. The very next day, the family cat suddenly sports a new haircut. Does it take Sherlock Holmes to solve this mystery? Hardly. Most weather mysteries are equally easy to solve once you understand the relationship between lapse rates and temperature inversions. The sun heats the earth, that's a fact. Very little of the sun's energy directly heats the air, that's also a fact. Then how does the air become warm? To incoming light, the atmosphere acts much like a pane of glass on a greenhouse, figure 17. It lets solar radiation easily pass through without absorbing much heat itself. This heat is absorbed by the Earth's surface. It's this heated surface that is primarily responsible for the atmosphere's heat content. As we learned in the beginning of this chapter, it's the surface of the Earth that heats or cools the air directly. On clear days, when the Earth absorbs an enormous amount of heat, the air in contact with the surface is warmed by touching, figure 18. As we move away from this heated surface, the air cools. We might say the temperature lapses or changes with an increase in altitude. Meteorologists call this the temperature lapse rate. It is one of the most important items in the science of meteorology. No one can guess exactly how much the temperature will change with altitude. In fact, meteorologists don't know, and they're paid to make scientific guesses. Many people think it changes at a steady 3.5 degrees Fahrenheit, or 2 degrees Celsius, per 1,000 feet. Not true. This is a misconception on the order of believing Pluto is a large dog orbiting the Sun. There are many variables affecting the rate temperature changes with altitude. To identify the rate of temperature change, weather specialists across the nation send up atmospheric test probes hooked to weather balloons twice daily. These probes provide information on wind, pressure, humidity, and temperature. Using this information, meteorologists are able to determine an exceptionally important measurement called the environmental temperature lapse rate. This lapse rate is essentially a vertical temperature profile of the atmosphere. Temperature change with altitude can vary considerably. It's anything but consistent. On a very hot day, the desert surface can reach temperatures of 150 degrees Fahrenheit, as shown in Figure 19. It's so hot that small animals standing too long in one spot can be seen exploding right in front of you. 4 to 5 feet above the surface, the air temperature may be only 90 degrees Fahrenheit.
That's an incredible lapse rate. Airplanes entering this shallow, heated layer of air during landing might experience turbulence as well as a decrease in air density. The turbulence is caused by thermals or updrafts, which are small little blighters of warmer air that your airplane bumps into. Crikey! This could make for a slightly less than smooth landing if the pilot wasn't prepared. It's also a great excuse to use with passengers if you land hard. Above the heated layer of air, this super lapse rate reverts to a rather normal, less dramatic temperature decrease with altitude. The depth, height of this superheated layer can increase during the day as warmer air from below rises and mixes with the cooler air aloft.
Figure 20 depicts several temperature-altitude plots for a clear day. At 11 a.m., the temperature plot tilts to the left immediately above the surface, indicating a dramatic temperature drop with altitude, point A. This is the result of a super-high lapse rate found over very hot surfaces. As altitude increases, the temperature decreases with a more normal, less dramatic lapse rate, point B. Later, at 3 p.m., the surface temperature starts off warmer, and a quick temperature drop is even more noticeable because of intense afternoon heating, point C. Temperature inversions. While it's common for air temperature to decrease with height, sometimes the opposite occurs. There are many occasions when the temperature actually increases as you ascend. This is called a temperature inversion, since the normal decreasing temperature lapse rate is turned upside down or inverted. There are two types of temperature inversions, a surface inversion and an inversion aloft. Surface inversion. The surface inversion, shown in Figure 21, is the most common type. It frequently forms around sunset and lasts until mid-morning. A setting sun allows the surface temperature to drop quickly, especially on cloudless, calm nights. In the absence of cloud cover, the Earth cools quickly in much the same way a heated waterbed cools when the covers are left off. There is nothing above the surface to absorb the radiant heat. Clouds, somewhat like blankets, prevent rapid surface cooling. The water droplets in them absorb radiant heat from the surface. As they warm, they re-radiate this heat back toward the ground, which absorbs the heat energy again. This exchange continues all night long and keeps surface temperatures warmer than they would be on a clear night. As the Earth cools, the air next to it starts to cool. In situations where there is not a lot of mixing, the layer adjacent to the Earth cools while the air above remains at or near daytime temperatures. The result is a temperature inversion. The base of a surface inversion, where the temperature starts to increase with height, is located at the surface. I'm just making sure this is clear. The top of the inversion occurs where the temperature lapse rate resumes its normal decrease with height. Typically, the top of surface inversions occurs within a few hundred feet of the ground. In case you think surface inversions involve sissy, wimpy little temperature changes, think again. Surface inversions can result in a temperature increase of 25 degrees Fahrenheit with a 250-foot increase in height above the surface. Even larger temperature differences are possible. Figure 22 shows several temperature-altitude plots for the late evening and early morning hours. At 6:30 p.m., a little after sunset in this profile, the temperature plot tilts to the right, position A. This means the temperature increases with an increase in altitude, up to a point. Then the temperature plot bends back to the left, position B. Where the curve bends to the left, the air is the warmest, position B. This is the location of the top of the surface inversion. Above the inversion, the air has a normal, decreasing temperature lapse rate, position C. The 5 a.m. temperature plot tells a similar story. The plot line starts at the far left of the diagram, indicating the surface temperature has cooled noticeably during the late evening and early morning, position D. As night progresses, the top of the inversion occurs at progressively higher altitudes, points E to F to G, as the layer of colder surface air grows. Remember, Figure 22 is a microview of the atmosphere. The altitude scale is in hundreds of feet. During winter in parts of Alaska, surface inversions can be quite impressive. Air at the surface can be minus 45 degrees Fahrenheit, while at 200 feet AGL, the air temperature can be minus 5 degrees Fahrenheit. This is a 40-degree Fahrenheit temperature increase in 200 feet, a very dramatic temperature change, somewhat like a Pompeian with a front-row seat at the Mount Vesuvius volcano trials. Long nights and short days contribute to this type of dramatic surface inversion.
Inversions with extreme temperature differences can cause pilots serious problems. Reports of very cold airplanes climbing into the warmer, moister air aloft warn of instantaneous frost formation on the windshield. This occurs in much the same way frost forms on a chilled drinking glass just removed from the freezer. Atmospheric moisture sublinates, bypasses the liquid state, going from gas in the atmosphere to solid on the glass, directly onto the aircraft's cold surface. At only a few hundred feet AGL, with no visual reference, no instrument rating, this has proven deadly to some pilots. Without wind to mix the warm and cold air together, a surface inversion is more likely to form. Winds of about 7 knots or greater can start mixing the warm and cold layers of air, causing the inversion to disappear. Little parcels of rising warm air, called convective currents because the motion is mostly vertical, from hot spots on the surface can help break up an inversion. This is why surface inversions forming over the desert seldom last past mid-morning, which is the time when convective currents typically start forming and begin mixing the air. You know what, Andy? I've always thought of convective currents as little unruly children who run up and down the stairs of the house, breaking things up. You know, several years ago, one of these little guys visited our place and tore things up. I told the little guy, "You better stop it or the devil's going to get you." He looked at me and said, "Well, why should I stop? I'm doing what he wants."
Inversion aloft. The other type of inversion is called an inversion aloft. These inversions are caused by warmer air moving horizontally over colder air and by air aloft that is descending and heated by compression. Figure 23. Unlike surface inversions, these inversions are typically found at higher altitudes, thus the word aloft. High-pressure centers in the atmosphere consist of large masses of air descending at rates of hundreds to thousands of feet per day. As this subsiding air descends, it experiences the same effect divers experience when descending to the bottom of a swimming pool, an increase in pressure. An increase in air pressure produces an increase in temperature for the same reason. Dough becomes warm when it is needed. I'm not talking about the dollar type of dough everyone needs. Compressing dough, or air, increases its temperature. The harder the dough is squeezed, the warmer it gets. If this descending layer of warm air comes to rest on a cooler layer of air, a temperature inversion can form aloft. This type of inversion is sometimes called a subsidence or subsidence inversion. In the summer months, a subsidence inversion is more common in the western half of the country than in the eastern half. In particular, it's quite common on or near the Pacific coast. When warm, high-pressure air subsides, lowers, onto the cool, moist inflow of air from the ocean, an inversion aloft forms as shown in the temperature-altitude profiles of Figure 24. A pilot faces a decreasing temperature lapse rate when departing an airport beneath the inversion. The climb is initially made in cool air, position A. Upon entering the bottom of the inversion, the air becomes warmer as altitude is gained, position B. At the top of the inversion, a decreasing temperature lapse rate is, once again, experienced, position C. Effects of temperature inversions. Recently, a friend and I went flying in a hot air balloon. We departed immediately after sunrise and ascended through the cool morning air. We rose so quickly it appeared that we were climbing at the best angle of bag, if there was such a thing, and of course there isn't. Suddenly, at approximately 1,500 feet AGL, the balloon ceased climbing. Figure 25A. Reaching the base of a temperature inversion aloft nullified our lift. The middle or top of a surface inversion can produce the same effect on a balloon, but at an altitude closer to the surface. Figure 25B. We just skipped along horizontally beneath the base of the inversion until more heat was applied to the balloon. In much the same way a temperature inversion impedes the ascent of a balloon, it can also prevent parcels of warmer air on the surface from ascending any higher. Have you ever noticed smoke coming from a chimney in the early morning or evening hours? Sometimes this smoke ascends for a short distance, then spreads out horizontally, as shown in Figure 26. The flattening of smoke is a sure indication of a temperature inversion. Since it's often seen closer to the surface in the evening, it's probably a surface inversion. Warm, rising puffs of smoke, much like a hot air balloon, cannot ascend through the warmer air of an inversion. In a similar way, the presence of a temperature inversion acts to flatten cloud tops. Therefore, layer-type clouds, otherwise known as stratus or straight-type clouds, are another visible indication of a temperature inversion, as shown in Figures 27A and 27B. More on stratus clouds later. The inability of smoke, haze, or pollution to move vertically and be carried away by the winds at higher altitudes reduces the local flight visibility. This is especially true in areas of industry, as shown in Figure 28. Mexico City rests in a large valley and is notorious for its temperature inversions. trapped pollution from the city can become so bad that asphyxiated birds have been known to fold their wings, croak, and just fall to earth. I wonder how many needless hours are spent plucking pigeons from sombreros. What to expect in an inversion? The visible signs of an inversion should cue pilots to expect several possible flight conditions. First, temperature inversions mean an increase in the likelihood of cloud formation. Since cool air exists at the surface, the air might start to condense, forming fog or low clouds. Second, visibility beneath the inversion can be quite low. Objects look farther away than they actually are. The mind equates something that is difficult to see with something being farther away. A natural response to this situation is to get closer to the item you're attempting to see. For example, under lower visibility conditions, pilots, thinking they are flying 5 miles away from the airport, are in all probability closer. They might be within the lateral limits of Class C or D airspace, while thinking they're avoiding these areas. In good visibility conditions, the opposite effect occurs. Pilots think they are flying closer to a specific point than they are, and tend to move farther away from a specific reference in good visibility conditions. Third, temperature inversions can indicate the presence of low-level wind shear. An inversion can allow a warmer, faster layer of air aloft to move, unrestricted by surface friction, Figure 29. Since warmer and colder air have different densities, they tend not to mix. That's why fancy restaurants like Jacques de Beau keep oil and vinegar salad dressing in separate bottles. They have different densities and don't mix. Given the proper conditions, the warmer air aloft can easily slip across the top of the cooler air, like skis on snow. Such a condition is conducive to the formation of low-level jet stream. This is where air within a few hundred to a few thousand feet above the surface can be moving at speeds up to 100 miles per hour. In the presence of an inversion, if surface winds are calm and winds at a few hundred feet to a few thousand feet AGL are in the 25-knot range, be prepared for possible wind shear. Wind shear is a condition where the velocity of the wind changes drastically over a small distance vertically. It can occur at all altitudes and in all directions and result in a sudden loss of lift. Large crab angles on the approach to an airport that's reporting calm surface winds are another clue to the presence of this wind shear. In other words, if the tower reports the winds are calm, yet you're having to substantially crab to keep aligned with the runway, be prepared for strong wind shear as you descend. I can think of no better time to add a few extra knots onto the approach speed for safety. Fourth, temperature inversions indicate the presence of stable air. Stability is the tendency of the atmosphere to resist vertical motion. In much the same way an inversion impedes the vertical progress of a hot air balloon, it also impedes the ascension of warmer air into the atmosphere, as shown in Figure 30. This is one of the most important points in the understanding of atmospheric stability.
Little parcels of warm air attempt to rise, but they cannot ascend into the increasingly warmer layers of air aloft, just like the smoke stops rising when it hits warmer air aloft. This means the atmosphere becomes smoother, because the warm parcels of air stop rising. A smoother, more comfortable ride is the net result. This is especially true when you're flying within the warmer air that rests on top of the cooler air at the bottom of the inversion. At this point, there is probably very little air rising within the warmer air, and you are not likely to experience any turbulence. Professional pilots know the most important tools for analyzing weather are visual cues, particularly haze layers, flattened cloud tops, and smoke levels. These are all flags signaling the existence of a temperature inversion. As the VOR is primary for navigational positioning, the thermometer is primary for meteorological understanding. Pay attention to the temperature when climbing or descending. Perhaps Abraham Maslow summed it up very well when he said, "If the only tool you have is a hammer, then everything looks like a nail." The more tools in your toolkit, the better chance you'll have of building a complete picture of the weather at hand. One of the tools you'll most certainly want is knowledge of how slight changes in lapse rate affect atmospheric stability.
Atmospheric stability: warm over cold, cold over warm. The atmosphere is stable when it resists the upward movement of air. It is unstable when it permits or amplifies this upward movement. In other words, stable air, if given an upward shove, sinks back to its original level. Unstable air, if shoved upward, continues to climb on its own. Atmospheric stability can be roughly visualized in two different scenarios. Figure 31a consists of a warm layer of air resting on top of a colder layer of air. Do these two layers want to change places? In other words, will the cold air on the bottom want to rise up through the warm air on top? This is unlikely. Cold air is heavy, more dense, and warm air is light and less dense. The atmosphere is stable, since these two layers are content to remain where they are. This explains why, after sunset, the air is usually stable. As the Earth cools, so does the air resting next to it. An upper layer of the atmosphere remains warm from heat acquired during daylight hours. Cold, heavy air is on the bottom and warmer, lighter air on top, a very stable condition. We know this condition to be a temperature inversion, and it explains why inversions are associated with stable air. Figure 31b consists of a colder layer of air resting on top of a warmer layer of air. Does this warm layer of air on the bottom want to rise up through the colder air above? Do golden retrievers want to eat dinner? You bet. Warm air rises, cold air falls. It's sort of like sitting on a balloon in the bathtub. You're on your own if you try this at home. You know that balloon wants to rise, and it will at the first opportunity. Warm air surrounded by cooler air will do exactly the same thing. I can't predict what the golden retriever will do. Cold on top of warm is a very unstable condition. As we've already seen with superlapse rates, a layer of air resting next to the heated surface of Earth can become quite warm. The vertical motion of unstable air produces turbulence. It also produces good visibility, as the rising air causes atmospheric mixing and helps disperse airborne pollutants. The Earth isn't heated evenly. The air next to the Earth's surface isn't heated evenly either. If it were, then entire layers of air in the atmospheric environment would move up and down together. In reality, layers of air don't do this. What actually happens is that some chunks of air become hotter than others. These air parcels break off from the surface and ascend individually as small blobs of variable sizes. Dust devils or isolated thunderstorms are often visual evidence of this happening. Glider pilots look for these rising columns of air with the same enthusiasm that carnival workers seek out tattoo parlors. So do hot air balloonists, who count on rising air for a free lift. Discovering one of these rising elevator shafts of air is their version of finding an engine in flight. The environmental lapse rate. I previously mentioned the environmental temperature lapse rate. This is the actual rate at which atmospheric temperature changes with altitude. Meteorologists also refer to the environmental lapse rate as the ambient lapse rate. These terms are used synonymously. I don't know why they don't just call it the real lapse rate, because that's what it is. Too simple, I guess. No one can predict what this environmental lapse rate will be. If they could, meteorologists wouldn't need to send up balloons at locations around the nation twice a day. Many aviation books will tell you the average lapse rate is 3.5 degrees Fahrenheit or 2 degrees Celsius per 1,000 feet, and this number is often used in calculations. Even the FAA uses it. Fine and dandy, but I want you to know it is as much a work of fiction as Jaws or New York on $3 a day. This 3.5 degree number is an average, which conceals a huge amount of variation, both horizontally and vertically. The 3.5 degree figure might hold true for 10,000 to 20,000 feet, then change to a different rate. It might remain true for 50,000 feet straight up over a shopping mall in Topeka, but be different if measured 15 or 50 miles away. See figures 31A and B. The lapse rate is highly variable from place to place, time to time, and even moment to moment. You can guess at it, you can approximate it, but in the end, if you want real information, you must measure it. With an understanding of the environmental lapse rate under your seatbelt, you're ready to use your aeroplane's thermometer to obtain a rough approximation of atmospheric stability. On your next cross-country flight, take vertical temperature measurements every 1,000 feet of climb. Ask yourself, am I climbing into air that's becoming warmer or colder? If you're climbing into warmer air, a temperature increase with altitude, then a temperature inversion is present. This is a stable condition. See Figure 31A. And no fancy calculations or advanced thinking are necessary. Enjoy your flight. If you're climbing into colder air, the temperature decreases with altitude, then atmospheric stability is dependent on how quickly the temperature decreases. If the air cools quickly as you ascend, then the cold air is above you and the warmer air is below. See Figure 31B. You can be sure these two layers want to change places. Some instability is sure to be present. Rising parcels of air. Let's consider those individual parcels of rising warm air we previously discussed. A warm parcel breaks away from the surface and rises into the cooler air aloft. As this parcel ascends, it expands, as shown in Figure 32. The air parcel expands much like a sealed bag of Fritos corn chips found in the back of your ascending aeroplane. Eventually, you reach the CFH, or critical Frito height, and the bag goes Frito Nova. Frito bags, like air parcels, expand because atmospheric pressure decreases with a gain in altitude. Basic physics decree that as a parcel of air expands, it also cools. This is one of the reasons why using a spray or deodorant early in the morning can cause you to moonwalk and make the Michael Jackson sound. The spray, which is rapidly expanding after being freed from its confinement in the can, cools quickly on its brief journey and forms a little glacier under your arm. A solitary parcel of air, moving vertically, also expands and cools with similar predictability. Here is an amazing and crucial fact of atmospheric physics. A rising parcel of air expands and cools at a constant rate of 5.4 degrees Fahrenheit for every 1,000 feet of climb, as long as that parcel remains unsaturated, in other words, doesn't form a cloud. Just to make the math a bit easier, we'll round that figure off to 5.5 degrees. For all practical purposes, no matter where you are on Earth, even the Bermuda Triangle, if you lift a parcel of unsaturated air, it's going to cool at about 5.5 degrees Fahrenheit for every 1,000 feet of altitude change, as shown in Figure 32.
But wait, I hear you saying, doesn't the rising parcel of air move through an atmosphere that also changes temperature? Yes, it does. But the rate at which the atmosphere changes temperature, you will recall, is inconsistent. It's inconsistencies that make things interesting, including the weather. Suppose we measure the environmental lapse rate with the airplane's thermometer, as shown in Figure 33. Our thermometer shows a decrease in temperature as we gain altitude. Which will cool most quickly, the environment or the rising parcel of air? As the Kung Fu master Caine would say, "Ah, grasshopper, now listen carefully.